Well, I'd like to thank the AETC, Brian, Tammy, Scooter, Harold, and the entire AETC crew. I think I've just covered most of them for the opportunity to come here and talk to you about bolts. What I want to do is, having done one of these before, the last one I did was Harold actually recruited myself and a good friend of mine and a consultant for us for many years, Carol Smith. It was 1999, I think, the last one we did in Colorado Springs. And it was the first one of these things that I had done, and I have to thank Carol for helping me get through that. And we tag teamed it in actual fact, and I think I only saw about 4 or 5 people actually do the first snore. So what I'm going to try and do is just, I was told I had to speak for 30 minutes and then do 15 minutes of Q&A. And when I first started to sit down and put this thing together and kind of tune up the old one, I realized that I thought it was going to be a struggle to talk for 30 minutes, and I realized that it's going to be a struggle to get it all in 30 minutes. So I want to try and get through some of the basic stuff. Again, keeping in mind the title of the presentation is to help you get the most out of horsepower and reliability from the fastener standpoint. We're going to try and canter through some of the principles. I thought you might find it interesting to know how the stuff is made. If you understand how it's made and how it works, you'll get a lot more out of it. So here we go. Again, so we're explaining the proper fastener strategy to maximize power and durability. Again, so we're going to cover basic fastener principles and terms, understanding the loads that are going on the engine from a fastener perspective, and then how to use the stuff, installation, tightening, preloading. So those are going to be the basic topics we're going to try and cover today. So, again, basic fastener principles. You know, nuts and bolts are something a lot of us take for granted, including myself, when I first started working at ARP right out about 20 years ago. My background was a race mechanic, so I used to work with this stuff on a regular basis. And when I started working at ARP, I realized that there's a heck of a lot to actually understand. So I thought we'd cover some of that. Don't want to assume that everybody knows everything about it, so we're going to cover some of the principles, how the threads are formed, how threads fit, and what makes them fit the way they do so that you can get the most out of the fastener. Again, the principle of the fastener is a spring. That's probably the best way to think about fasteners, because obviously by tightening the threads, you're going to create a clamp load, which is what holds everything together. So we're going to talk about that, preload, clamping load, the stretch versus load relationship. And then we're also going to talk about modulus stiffness. Modulus elasticity does not change regardless of heat treatment. We'll cover that too. When I get done at the end, obviously there's going to be an opportunity to ask questions. If I could ask you just to make notes, and we'll get to that at the end, and I'll try and answer any questions you have. So, talking about thread terminology, again, it helps to understand what some of the terms are. During the course of the presentation, we'll be referring to different terms. And again, some of the basic principles are things that we shouldn't overlook. So, again, these are the basic terms that we're going to use when we talk about threads. We've obviously got the minor diameter here, the pitch diameter, which is probably the most significant part of the thread geometry, and obviously major diameter. And then obviously the pitch of the thread is the distance between one point to the next, either the peak of the major to the peak of the next major, or from flank to flank. These are some of the things we'll be talking about. Next, we'll talk about thread forms. And this is a question that comes up a lot at ARP when people talk to us about different thread forms and the difference in thread root profile, which is this area right here. So this is a standard UNF form. This would be something that you would see on a commercial bolt that you'd buy at a hardware store or motor factory or whatever. And if I toggle to the next slide, you'll see, if you focus on this area here, again, you're going to see a pretty big difference. So this is a J-form thread, and obviously by having a large radius here, It really helps with stress distribution and reducing the stress concentration in that thread root. So that's something that you should probably be aware of when you're putting an engine together. Obviously, in certain applications, the most critical being the connecting rod, there's a lot of bending and fluctuating loads that go on there. So when you've got any kind of bending or fluctuating load, if this is the smallest diameter, this is where all that bending load is going to be going on. So again, if you've got a large radius there, you've got less stress effect on that area. So when people talk about thread fit, and this is something that we've probably all done, you pick up a nut and bolt or a stud and you put a nut on it. Everyone likes to feel that. And it kind of is either a confidence builder or a confidence killer. If the thing feels loose and sloppy, you're not going to really feel really good about putting the thing together. But obviously what determines the fit is effectively if you've got two wedges here. This is your internal thread, this is your external thread. And obviously the pitch diameter, which is this line right here, by reducing that diameter, keeping this one the same, you're going to have a sloppier fit. So basically you're talking about the intersection of two wedges and how closely they fit into one another. All of the threads that we roll are 3A if it's male thread, 3B if it's female. There are several classes of thread. The two most widely used are commercial class, which would be a 2A male or a 2B female, and then the tighter tolerance is the 3A, 3B fit. That's what we work with typically. And in that pitch tolerance, you've got about 0.003 tolerance between those two diameters. So obviously there's not a lot of room in there when you actually start to assemble things, which of course is another reason to make sure everything's clean before you start assembling. So moving right along, the next thing that I thought might be helpful for some of you to know is how threads are formed, because when we do show people around the shop, some people really have absolutely no idea how a thread is formed, and it's actually pretty straightforward and pretty interesting how it works. So we use all the threads that we produce are thread rolled, and there are two types of machines, either a 2-die flat roller, which is what you're seeing here, and I've got a video that'll we're going to put up next that'll see how it works. And then the other form is a 3-die cylindrical thread roller where the 3 dies are on a cam and the dies move in and out. So I'm going to run a quick video for you. It might just take a second to load, but...
Well, this is a thread roller, and it's a 2-die machine, so there's 2 dies that have thread. The threads are on each side, and the operator places the part in the machine, and then the other die comes across, and it rolls the threads into the machine. So it's pressing, forming the threads into the part without cutting anything. This is a tri-roll. We saw the 2-die machine where it's a flat roller and it uses flat dies. Right. Well, this is a 3-die cylindrical die machine, and the dies are operated by a cam, and they open a part. The operator puts the part in, and they come together, and they're spinning, and that's what rolls the thread onto the part.
So hopefully that gives you some insight into how the threads are formed. Again, it all helps, I think, when you understand what you're working with and how to get the most out of it. So again, looking at the fastener as a spring, and that is the way you should look at all of the fasteners. Obviously, all metals are elastic. They have elastic properties. The more you pull it apart, if you think of it in the terms of like a carburetor return spring, obviously the more you extend the spring, the more clamp load you get, up to a point, and that point being the yield. And we'll get to that here in a minute. Obviously, you've got to generate a preload, and your preload has got to exceed your dynamic load. Otherwise, you're going to have failure. You're going to have joint separation, or you're going to have a blown head gasket, or you're going to have main caps walking around. So again, just keep in mind that the preload is what we're trying to achieve when we're tightening the fastener. So the next slide here shows the relationship between torque, tension, and preload. So what we see here is these are actually the results from, we actually have a CNC-driven load cell that we use to develop different fasteners, different techniques, and different lubricants. So what it's doing, basically, it captures three channels of information. We've got, obviously, clamp load here in pounds. It also records the degree of rotation, because we're all familiar now with torque and angle tightening techniques, and we can cover that a little bit later on. And then it also records the amount of torque required to achieve that clamp load. So we've got a tension line here, and we've also got a torque graph here. In this particular case, we're installing to the max load that we've got here is 17,000 pounds. That's where the thing starts to flatten out. We want to be working always in this portion of the graph, because this is the elastic portion of the fastener here. When we get into this area right here, we're working in the plastic. So when you get a torque to yield fastener, this is the area that they're trying to get you to move into. And from an OEM standpoint, this is a lot easier to achieve because obviously their joints are all designed to work at a certain clamp load. And this represents a much bigger window of opportunity to make sure you're going to get the clamp load that you need. Whereas on this portion, the straight line portion of the graph, you can see that a relatively small amount of torque has a fairly big effect on the clamp load. So again, with OEM, they're trying to get a clamp load, let's say that's arguably 17,000 pounds of clamp load, that you've got, if you look at the amount of rotation of angle here, you've got a pretty big window to get into that kind of clamp load to make sure that that joint is going to work correctly. All of our fasteners that we use are designed to be reusable, so we're always working in the elastic portion, and we typically always pick a clamp load figure that's based on 75% of this point, this being the yield point right here. So we're going to be working in this sort of load here. So for us, it's a question of understanding the load that the fastener is going to see. Very often, the size of the fastener is dictated by the design, so we don't have that luxury very often. So then it's just a question of finding the right material that's going to give you the strength to be able to work in this portion. One of the other things that comes up quite frequently for us is if you make the fastener harder, if you take it to a higher hardness range and therefore a higher tensile strength, doesn't that also make it stiffer? And the answer is no. And what this slide demonstrates basically is that we've got 3 different materials here. We've got actually 5 total. This is our 8740 material. This is kind of bread and butter standard material. This is 190 KSI material. So when you perform, this is actually a straight tensile test of failure graph, what you're seeing here. The only thing that changes is we've got a material here that's 190 KSI. We've got one here that's 220 KSI. And we've got a custom age here that's 260 KSI. As you can see from the slope, the relationship or the rate at which they stretch is all exactly the same. Because they all, if you're looking at the rate of stretch, we've got clamp load versus extension here. This is how much stretch is going on in the fastener. In actual fact, you'll notice here that these are some pretty big numbers. That's because our tensile test machine actually records the total measurement of the fixture, not the stretch that's going on in the specific fastener. So this is off by very roughly a factor of around 10. But it still demonstrates the modulus here. So the rate at which the fasteners stretch is exactly the same. The only thing that changes is the yield strength. So by raising the tensile strength, you're raising the yield strength. So the yield point here, yield point here, yield point here. The exception to the rule here, and again, which also demonstrates the modulus, is this material here, which is MP35N. This has a modulus of elasticity that's about 12% higher than the other 3 materials. So again, the rate at which it stretches is different. So this particular material is stiffer. But all these other materials, again, the rate at which they stretch is the same. All you're doing is raising the yield strength. So it doesn't make it, just by having a higher yield strength, doesn't make it more resistant to stretch. So we're talking about understanding the loads. Obviously, the most highly loaded joint in the engine is the connecting rod. That's seeing at extremely high loads, and obviously that's dictated by reciprocating weight and RPM. The other thing, of course, we got is non-reciprocating loads, so things like cylinder head, mains, main studs or main bolts. Now, I threw this slide up here to be politically correct. I've put up actually this is a GM LS7 titanium connecting rod, but The reason for putting it up is to point out that obviously when the thing's running at RPM, there's actually a bending load that goes on in the big end of the rod here. So at top dead center, obviously you've got a load that's being exerted by the piston and the rod trying to throw itself off the crank. What that does effectively, it puts a bending load at the parting line. So if you think of if you were to take an O-ring and hold it in your fingers, and you put your fingers in the top and the bottom, as you pull this way, it pulls the sides of the O-ring in. That's exactly what's going on the connecting rod. So there's a bending load that pulls the joint on the mains journal here towards the journal of the crank. Obviously, there's only so much clearance in there because of the oil clearance between the bearing and the journal. So it's a very small amount, but it is significant in that you've got a bending load that's going on that bolt. So the bolt is basically being bent in this direction every cycle. That is what we call a fatigue load. So it's either a bending or a fluctuating load. Obviously, in this case, it's a bending load. There is no fluctuating load as long as you've got the preload right. As long as you've picked the right material, the right fastener for the job, you want that preload to exceed the dynamic load. And that's one of the things that we go through with customers on a regular basis. If they call us and say, what bolt do I need to run? There's some very fundamental information we've got to get from you to understand what the load is going to be, and we can calculate that. This is what happens when you get it wrong. So we've got a failure here this is a fatigue failure as a result of either picking the wrong material or from not having the fastener preloaded correctly to where the dynamic load and the bending load exceeds the fatigue life of the material. So what happens is you can see the origin, you'll start a fatigue crack here. Obviously, if you think about the paperclip analogy, if you bend that thing backwards and forwards, it's going to fracture and break. So you start with a crack initiation, typically on the inboard side of the rod, because if you think about the bending load that's going on, the largest concentration is going to be the inboard side of the bolt. And those cracks open up and ratchet. So you can see these striations going across here. So each time that the joint gets to a load that exceeds the load, the clamping load within the bolt, it's going to open that crack up. On the downstroke, it's going to close back because the load is relaxed. As it gets to top dead center again, that crack's going to open up. And that crack keeps opening up and ratcheting. And these lines show the travel of that crack. And you can see we've got to the point here where you've gone more than 50% across the face. So you've got a very, very tough ductile material here. If this were a very brittle material, you'd see one crack and then it would be over. So you can see that this thing went through hell, basically, before it failed. So finally, into this area here, you've got dimple rupture overload, where there's just so little material left that it just can't hang on anymore. So one of the things, obviously, avoid this is to make sure that principally you've got the joint tightened correctly, and we'll talk about that next. One of the other things important to remember is the difference between a bolt that's rolled before and after heat treat. And what you can see here is, this is actually a slide that I found on the web. This isn't actually one of our threads, but you can still see the same thing. The difference between rolling the thread before and after heat treat, as we saw from that video of the threads being rolled, you're exerting a huge amount of compressive stress on that part in order to form that thread on there. Tremendous amount. And what you can see here is that cold working here. You can see the grain here, how the grain is compressed in this area right here in the thread root. So that cold working effect is something that we want, because if you look at the simple analogy of taking a piece of mild steel and putting it on an anvil and hitting it with a sledgehammer, you're going to compress that grain, you're going to make the material stronger, and therefore you're making it more resistant to cracking. With a commercial bolt, something that you'd buy, say, at a hardware store, the parts are thread rolled before heat treat. So they're forged, they're thread rolled, they're heat treated. Obviously, when you're rolling a part that's soft, you're going to get a lot more die life. It makes it a lot more cost effective to produce. And they're perfectly okay in the right environment. Obviously, where you've got a joint that doesn't see any fatigue load, it doesn't really matter that much. But in a joint where you do see fatigue, especially in a connecting rod, you definitely want a part that's been rolled after heat treat. We get people, I can remember in the early days of working at ARP, I'd get people who typically, aerospace goes through dips and peaks. in the dips, you get a lot of machinists that now are looking for work, and they think they're going to start making connecting rods. And they'll go out and they'll design a rod, they'll machine it, and they'll put cap screw connecting rod bolts in. They'll just buy an Allen head cap screw, and they give it to whoever's going to try it, and they break, and they're just gobsmacked that they can't believe that it failed. The biggest reason is because, again, they've got no compressive stress at the thread root. So it's important to understand that significant difference. So on this slide here, basically what I wanted to demonstrate, and this question comes up a lot, what happens if I just bring the speed up of the engine? If I increase the RPM, what is going to be the effect on the joint? As you can see, fairly small increases in RPM have a very significant increase on the load, because the load on the cap goes up as a square with the RPM. So it's a very significant increase. So here we've just got a typical kind of scenario. We've got the reciprocating weight, which includes everything from the split line of the rod up. So we don't include the cap or the bolts, but everything that's trying to throw itself off the journal of the crank. So it would be a complete piston assembly, rings, locks, pin, and the beam of the rod. So we have to understand what that weight is. We have to understand what the stroke of the engine is and the length. That then determines the acceleration. And we've got the RPM. And as you can see here, very, very big increase for not a huge increase in RPM. So always keep that in mind too. Don't just assume that, oh, I'm just going to bump it up 500 RPM, I'm going to be fine. Hopefully, if we've all done our sums right, meaning you and us, it shouldn't have any effect. But if we're on a marginal situation, this is very significant, obviously, and if you get it wrong, then obviously you're going to get a failure. And although you might have a joint that will withstand this kind of load, the problem is that the fatigue life gets dramatically shortened as you get really marginal on clamp load. So let's talk about installation techniques, and that really kind of harks back to the title of this whole presentation. How can you get durability out of the engine? Obviously, we all know that the straightening or the tightening methods that are out there, they all have their place, they all have their merits, they all have their pitfalls. Obviously, straight torque is probably the most commonly used. Torque and angle can be used even in a situation where you're going to reuse the fastener. Obviously, you just got to be aware of where the yield point is. You don't have to take it into the yield to make it work. Torque and angle basically, of course, is a step forward in accuracy from straight torque, because with straight torque, you're just concerned about friction. That's all you're doing. You're estimating what the friction is, or frictional resistance is going to be to achieve a certain amount of stretch. And obviously, that's mostly affected by the lubricant that you're using, but also the surface finish of the surfaces where you're going to be generating the friction in the threads and on the spot face of whatever it is that you're working on. And then we've got stretch. Well, stretch, of course, is great when you've got access to both ends of the vault. And the most common place there, of course, would be the connecting rod, and probably the most significant. So it's definitely the most useful technique and the most accurate technique to use for assembling the connecting rod. So, again, all the lubes out there have different friction coefficients, and again, this is a common question that comes up almost on a daily basis. Well, what if I use this lube? What if I use Redline assembly oil? What if I want to use Loctite? What if I want to use motor oil? And the machine that you're looking at here is, this is the load cell that we looked at the graph that was produced earlier. So it's, again, CNC driven. This is the controller right here. It's a DC motor driving through a torque multiplier, through a torque and angle transducer here. So we're picking up 2 channels here, and then the channel here, which is measuring the actual clamp load. So the fastener is actually in this part right here. This is the socket that drives the nut or the head of the bolt. This is the fixture that holds the backside, either the nut or the nut plate. And this is the machine that we use to develop a lubricant that we came out with probably about 3 years ago now, which is our Ultra Torque. Maybe some of you are familiar with it, some of you might not be. I'll show you a quick video here. that demonstrates the difference between the lubes and how they work.
Hey, welcome back to Horsepower and a little heads-up tech segment we're calling Bolt Basics. There are hundreds of bolts and studs in a typical engine. Stands to reason, then, that using the best quality fasteners, proper torque specs, and lube are critical to keeping everything together, especially for high-performance use and abuse. Of course, there's a lot more to it than knowing righty-tighty, lefty-loosey. In fact, what happens between the first twist of the bolt and that last click is often a mystery. All metals have some elastic properties, which means they can be compressed or, more importantly, stretched. When a bolt or stud is stretched, it has a natural tendency to return to its original length. That's why when you torque one down, you're trying to stretch it just enough to add a clamping force that'll keep it in place. This is also known as preload. Maintaining and achieving a bolt's proper clamp load is all about overcoming friction, and even ARPs can't do that without the right lube. There are a lot of choices out there, but using some of their studs and this strain gauge, we're going to test some different results. First, good old motor oil on the threads of this ARP stud and nut, which has a torque value of 125 foot-pounds. So when the torque wrench clicks, the gauge needle should be at 18,000 pounds. And on the first cycle, we're at 15,000, not enough. And eventually we do hit the target, but only after several cycles. Next, with a new identical stud and nut, the ever-popular Molly lube. And once again, when the torque wrench says we're there, we're really 3,000 pounds under. Several cycles later, we're at 19 and a half, about 1,500 pounds over the target. This is a lube commonly called peanut butter. It's used by a lot of top fuel race teams who torque their stuff down once, make a 5-second pass, and then tear the engine down before the next run. I can see why they use it. It torques down at 18,000 pounds the first time. However, it's not recommended for street strip engines because on each follow-up cycle, the gauge goes up several thousand pounds above the target. On about the 7th cycle, we're all the way up to 30,000 pounds. Uh-oh, that wasn't the torque wrench. Now let's see what we got here. Now that sound was obviously threads letting go inside this nut, and it's not going anywhere. Imagine if this was in your engine. You'd be screwed, no pun intended. Finally, ARP's Ultra Torque Lube, made without moly or metals, and formulated to achieve the target preload on the first torque cycle with repeatability. Plus, it prevents seizing and galling on threads. On the first torque sequence, we're at 18.5, which is right in the ballpark. But ARP claims Ultra Lube will maintain that preload level within 5% on all following torque cycles. And it does on the second and the third, and for 2 more cycles before we call it quits. Other recent tests measuring rod bolt stretch with different lubes revealed pretty much the same results we got. So, while using quality fasteners and the proper torque specs are critical, it's the lube that lets you hit that target preload and hit it consistently. Today, this ARP Ultra Torque was the only one that really made the grade.
You're watching Horsepower.
So let's talk about stretch versus preload. We're talking about the stretch relationship. It is a straight line. So at any given point, if we know how much stretch we've got in a specific fastener, and the stretch is pertinent to each fastener design, it's obviously driven by the yield strength, by the modulus of the material and the cross section. So you're looking at, on say a connecting rod bolt where you've got an undercut or a wasted shank bolt, you've basically got 3 areas where you're calculating based on the mass of material that's there, what the stretch is going to be. So you've got 3 distinct areas. You've got the shank underneath the head, which is typically the nominal diameter. You've got a radius then that blends into the undercut or the wasted shank, and you've got the threaded area. So by taking those 3 areas and calculating what that mass is, unfortunately, we've got a very clever mechanical engineer that's written a program for us. We can calculate what that ideal stretch should be. And again, it is a straight line relationship. So at any given point, if you know how much stretch you've got based on that specific fastener, you know how much clamp load you've got. And obviously in a connecting rod, one of the quickest and easiest ways to record that stretch is using a stretch gauge, either ours or somebody else's, it doesn't really matter. The most significant thing is that in this situation, you obviously got a dial indicator here. A standard dial indicator has a very weak spring because it's just designed to measure difference. In this instance, we need a lot of spring pressure because we've got to get the points to register in the 45-degree or 90-degree included angle at the bottom of the lightning hole, and we also put a 90-degree center drill dimple in the other end. So in this situation, you can very easily install the bolt by stretch. There's a number of different ways of doing that, and different people like doing it different ways. One of the ways that I like to do it in the shop is actually to put a box end wrench on the fastener, put a long extension on it, unless you're a gorilla and you can actually take that pain, but then put the stretch gauge over the top, and then just pull on the wrench until you see the stretch that you want, and you're done. So it's a very easy way of doing it. And again, I can't overemphasize the importance of getting the correct amount of stretch in a rod bolt, because it's the only guarantee you've really got of knowing how much clamp load is on the joint. And that is it. I don't know how close I am to 30 minutes, but I'm probably a little under. So,
Please. Thank you very much, Chris.